Hello everyone, this is New Ye from Nanyang Technological University, Singapore. In this talk, I will present our work on finding smart contract permission bar with role mining. Smart contracts are computer programs running on blockchain. Smart contracts have been used to manage valuable assets. For example, users can buy and sell the smart contract powers standard ERC20 tokens and NFT tokens. Generally, smart contracts involve multiple types of users with different capabilities. For example, someone can be the owner to manage the contract while others are not. On the other hand, smart contract execution runs on its own code. However, once deployed, some contract code cannot be changed. Therefore, it's essential to enforce asset control policy correctly for smart contract implementation. Here, we present an asset control example for a decentralized financial application named ValiDeFi. ValiDeFi is used to exchange different types of tokens at a price between users. And its pool contract involves 4 types of users. The first one is operator, who can initialize a pool contract. Exchange process performs trading tasks on behalf of the users, such as depositing funds of users. And the job of fund agent is to allocate accumulated profits among users. The last one are normal users. They can deposit some tokens into the contract and then withdraw it. Now I have briefly introduced smart contract and its access control usage. For the remaining part of this talk, I will show a permission bar smart contract and present our approach to find such permission bars. Later, I will show our evaluation result and conclude our talk in the end. The show example is from a decentralized financial application, ValiDeFi. They have a pool contract containing a permission bar in its initialized function, which later caused a $6 million loss. In the initialized function, it has 3 input parameters: state token address, liquidity token address, and reserve fund address. The purpose of the function is to configure 2 token address for state token and liquidity token. And it also sets the variables, reserve fund, and operator. Specifically, the operator will be set as the messenger who calls the initialize function. Moreover, initialize function has a modifier not initialized in smart contract language, Solidity. Modifiers are used to validate input to restrict user access. The not initialized modifier implies that when the variable initialized is false, initialized function can be accessed. However, there's a permission bar here. Any user can call the initialized function multiple times and make himself the contract operator. The bug fix is to add a statement to set the variable initialized to be true at the end of the function. The pattern-based approach can be divided into static analysis and dynamic analysis. Static analysis would check if there's any modifier to protect the smart contract. However, the initialize function is protected by the modifier not initialized. Static analysis fails to realize that not initialized modifier will always return true, thus making the initialize function unprotected. Dynamic analysis needs to the predefined test oracles. However, it lacks contract-specific test oracle on which type of user may invoke the initialize function. Although model-based approach can be complex and solved, this approach requires user to provide specification model. On the other hand, to find permission bars, we need to know access control policy of smart contract and then perform conformance checking between smart contract implementation and access control policy. However, the main challenge confronted with us is how to get access control policy of the smart contract. Most smart contract lacks the specification to describe its access control policy. So we propose to learn the access control policy from smart contract transaction history. Now I introduce our approach to find smart contract permission bug. First, we extract user access knock from transaction history. Each knock is a tuple consisting of user and access function. Then, with the user access knock, we use genetic algorithm-based row mining to learn the row structures. Next, we infer the access control policy based on the information security lattice of these rows. Last, we perform conformance testing to find permission bugs in smart contract intentions. Let's walk through our approach using an example. First, to deploy smart contract, developers submit a transaction for contract creation to blockchain. Once the transaction is executed successfully and included in the block, the smart contract has been deployed on blockchain. The history will record this transaction as well. Then user A call initialize function to configure state token and liquidity token. Transaction history will record that. Similarly, user A can also call second exchange deposit function to configure the fund agent of the pool contract. The similar is for other transactions. The last user, F, deposits some tokens to the pool contract. Now we have 11 transactions in the history. With the user access knock from transaction history, we can perform row mining to learn row structures. To do this, we first construct user access matrix. The matrix records a mapping from user to functions. Each cell shows if a user has access functions. For example, the user who called both initialize and set exchange policy function. Most row mining algorithms learn row structures from user access matrix. However, the contract transaction history is usually limited. Therefore, user access knock is also incomplete, and that is, some users have permission, but they have not yet called some function. In this example, we know last user called deposit function. He could, but has not called withdraw function in the transaction history. To address this problem, we need to mine user roles of smart contract from partial observation. Our intuitions are that users belong to the same role if they have same access functions, or they have some functions in common, and they also show high similarity in the usage frequency. However, there are some challenges here. First, for a role, if we consider the users with the same access functions only, there will be too many spurious roles. But if we also consider similar users, there will be too less user roles, and there's a large mismatch with observations. Last but not the least, row mining problem is NP-hard. So we propose a genetic algorithm solution to do the row mining. We introduce two metrics to balance the number of user roles and the mismatch with observations. The frequency similarity matrix is to measure the chance of a spurious role, and the consistent metric is used to measure the mismatch with observations. Our row mining has two steps. First, we create the basic rows with the same set of function calls. Then, some basic rows need to be merged according to the row similarity and the consistency. According to these steps, we can get 4 rows. Each row is constructed by a set of users and a set of functions. Normal user includes 3 users, and they have the permission to call deposit and withdraw function. Here we show the complete row structure in the table. There are 4 rows. Operator rows has the permission to initialize the contract, set the contract operator, set exchange policy, and so on. In smart contracts, the objects we care about the most are contract state variables. The records critical information such as the balance values, row assignments, and asset prices. So we analyze the written state variable by these rows. Our access control policy can be constructed as the information security lattice based on the written state variables of these rows. The upper row has more permissions than the lower one. For example, normal user cannot write critical variables, while the operator can write the most critical variables. With the access control policy, we can then check smart contract implementation to see if there's a permission bug. Our conformance testing will use existing symbolic execution engine provided by Manticore. We extend it by the integration of concurrent value from blockchain snapshot, such as the latest state variable values. Based on control dependency analysis of smart contract functions, we generate 4 test sequences. Each test sequence consists of 2 function calls. We assume attacker is from the normal user. Any violation against the information security lattice would make the access control policy unsafe. The first test sequence fails because section policy function cannot be executed successfully. Therefore, the access control policy is safe. Similarly, the second and the third test sequence is safe. For the last test sequence, attacker calls the initialize function. Since the initialize function is unprotected, so the contract operator can be initialized by the attacker. The attacker calls set exchange policy function to change the reserve fund state variable. And this would change the fund agent to be the attacker too. Therefore, the last test sequence is an employee attack sequence, and we can generate concrete transaction at the POC. We evaluate our approach to answer 3 research questions. First is about accuracy and efficiency of the proposed row mining. The second is the performance in permission bar finding. Last is to discuss why existing tools fail to detect many permission bars and how our approach improve on this. To evaluate the row mining, we manually collect our row mining benchmark for smart contracts. We search all smart contracts whose source code using the access control template provided by OpenZeppelin. This contract is using only row or has row modifiers to label function with row. We compare our tool with 4 row mining techniques. Our row mining using genetic algorithm based on frequency similarity metric and consistent metric. We try 3 different weight configurations. Basically, we hope the number of mined user rows is close to that of ground truth. Overall, our algorithm mines next number of user rows, which is closer to the number of the ground truth. Therefore, SBCon works better compared to the existing techniques in row mining for smart contracts. Further, we evaluate how SBCon can be used to find permission bar and compare it with existing tools. We compare it on the benchmark smart bars. Smart bars benchmark is a public data set consisting of more than 40,000 contracts from the Ethereum blockchain. The results show SBCon has high agreement with the existing tools and the highest true positive rate. Moreover, SBCon found 11 previous unknown permission bars in the benchmark. A CVE is a confirmed bar report. There are more than 500 smart contract CVEs and 19 CVEs are permission bars. We compare SBCon with existing tools on the 17 CVEs. It shows SBCon can detect 9 CVEs, which is much more than any other tools. We also investigate the reason why the current tools fail to detect some permission bars. Most tools are pattern-based. The patterns they use are limited and overly generic. For example, static analysis tools will check if there are modifiers to protect function. For our approach, we can learn likely access control model to a specific contract. The model can be used as a patterns or test oracles to find a wider range of permission bars. Let's conclude this talk. We propose an approach to find smart contract permission bars with row mining. We learn permission models from transaction history and generate executable exploits to the permission bars. That's all. Thanks.